Swayam Prabha. Digital India. Educated India.
Good morning, and it's very nice to see all of you here, and many for attending this course. And first of all, I would like to thank Ravi for the nice introduction to me. And as Ravi mentioned, that I've been to IIT Madras many times during my visit to India, and I know Ravi for maybe close to 30 years. And also Professor Lakshman for arranging this Gian course together with me. And he invited me actually for applying for this Gian course and arranging this. And thank you very much for that. And it's a great pleasure for me to be here for this course, these 5 days. I also had a Gian course earlier as well, so I'm familiar with this program. And of course, that course was not on corrosion, but was more on advanced materials earlier. And today we are going to talk about corrosion. So that's the theme today. And so the title what we put was Corrosion Prevention Control and Importance in the Era of Sustainable Development. And the reason that we thought of having this title and this theme for the course is that I think probably many of you are aware of that corrosion is becoming a big issue when new sustainable technologies are coming up, and everybody is looking for low carbon, low CO2 emission technologies, and in that front, there are wind turbines are coming up for energy production which produce less carbon dioxide, solar energy, and geothermal energy. Hydrothermal energy also in different ways, using the hydro storage as energy storage mechanisms, and power to X, like the power to X include everything that is electrolyzers, fuel cells, and things like that. And everywhere, if you and on the other side, also the electrification in the automotive, and everywhere, basically what is happening is corrosion is the main blockage, or we can say that the bottleneck in relation with the material use, and that way these technologies are suffering from efficiency issues because of corrosion and things like that. So corrosion is becoming a big topic, and because at least in the West, if you take the Europe, because they are focusing much more on the sustainable technologies, it's becoming a big topic. So I think it is apt to discuss about this corrosion, sustainable technologies, this relationship, and that is mainly what we are planning in this course. And but I'll go to the little bit more detail about the program. But before we go to that, I just want to tell a little bit about me and where I come from. So I come from, as Ravi mentioned, Technical University of Denmark, which is quite old university, as you can see, that is established in 1829 by this Danish physicist called Hans Christian Ørsted. And probably you know by the name of this one, Ørsted, because if the magnetic field is, the unit of the magnetic field is Ørsted, it is because of this. Because he is the one discovered the relationship between electricity and magnetism. So he is a famous physicist. So he established in 1829. And so we are located very close to the Danish capital, that is the Copenhagen, which is around 15 kilometers away from the Copenhagen. And you can see that is the yes, and it is a little bit 15 kilometers away from the Copenhagen, so that's a campus view. It is almost like one campus university, and although there are few things outside this campus, and otherwise it is most of the things are 80% of the university is located at this place. This Danish physicist Hans Christian Ørsted also has a relation to the metallurgy, because he is the first one discovered aluminium, although he didn't realize that he discovered an important metal. It took 100 years after that, the aluminium became a commercial metal, but he discovered it first. Only thing is that his process of extracting the aluminium didn't become a commercial process because he extracted aluminum using the amalgam route by using mercury, which never became a commercial process. But he could extract the metal and see that this metal has certain good properties, although he didn't realize that he's discovered the second biggest structural material that we use today. So that is also that way he also has connection, little bit connection to the metallurgy. Our university, like technical university, is more like IIT. We have only engineering, science, technology, and management. We don't have other faculties. So we have about 13,000 students these days. It's a very international campus. We have people coming from more than 100 countries in the faculty side as well as from the student side. And we also have a very big number of percentage of women in the workforce, in the students as well as faculty again. You can see that almost half of our master students come from outside, and it is also the case, same case with the PhD students. Not even half, maybe 70% of our PhD students are from outside. In my group, only international PhD students are there, no Danes, actually. So that's the way that way it's a very, very international campus, and so that is very nice also for the international students when they come there. And my department is Department of Civil and Mechanical Engineering, which is also called D2 Construct. But the more important thing is that within this is a big department to administrative purpose. They put together many things. And I belongs to this section of Materials and Surface Engineering. And that is a division within the department, and where we work on materials, corrosion, microstructural issues, and things like that. Not mechanical metallurgy and extractive metallurgy, because mechanical metallurgy and extractive metallurgy is with another section like that. So there's a solid mechanics and mechanics section, and also there is a manufacturing section, so the casting and all is with that. And within the section of materials and surface engineering, we have a very big corrosion research program, and that's my group. And we work in our key focus area is these three of them, although sometimes we'll have projects in related to other things, but a key research area is these three of them. We work on aluminum and corrosion area, and these days we are focusing on aluminum recycling part, because aluminum is a big material today, again related to sustainability. We are also going to talk that later as well, because it's very light. So that means that if you use aluminum in any structure, we can increase the efficiency because of reduction in the weight. The problem with aluminum is extremely costly compared to steel. The virgin aluminum costs probably 5 or 6 times of steel, so that way it's not profitable to use. So the only way aluminum can be pushed into the products to replace the steel is that you need to recycle. Recycled aluminum is much cheaper because it's spent only 5% of the energy. So, but recycling also comes with a lot of problems. That's a good thing for the good or bad things for the metallurgist, because it has microstructural issues. When you do the recycling, a lot of impurity will get into the aluminum, and that will have corrosion problem. And so that's one of the key things which we are looking. Our collaborator here is Hydro Aluminium, which is one international aluminum company, but the main part is in Norway, this Hydro Aluminium. We work with carbon capture and storage related corrosion issues, because now everybody is discussing about capturing the carbon dioxide and pushing it somewhere. So you capture the carbon dioxide. If there is a power plant which is emitting carbon dioxide, you capture that, pressurize into a liquid form. And when I say liquid form, it is more in the supercritical form. Supercritical form is like a liquid, but in between gas and liquid state. And because why they wanted the supercritical form? Supercritical form is easy to transport compared to the liquid form or gaseous form. So just change it to a supercritical form and then pump it down. Any hole, you pump it down, and that means that you have taken the carbon dioxide from the atmosphere more or less and put it down. So that way you can reduce the carbon dioxide level in the atmosphere. So this is a big thing in the West. In Europe, there is a lot of focus on that. And where to put it? The best place to put it is the oil wells. There are many oil wells where oil is extracted, it's empty. Now, nothing to do with those wells. And so the reservoir is empty because oil has taken out. Push the CO2 there and close it. And you can put large amount of CO2 there. So in Denmark, there is North Sea. In the North Sea, they were producing a lot of oil. Now many of the oil wells are empty, so they push it there. And our collaborator there is Total Energy, which is one of the big energy companies. is originally a French company, and they are entering oil and gas company actually, but they are entering into carbon capture and storage. They want to make it as a business, carbon capture and storage, and they are our collaborator. Another collaborator is this Wintershall Dea, which is also in this area, which is a German company, again an international company, and these small companies which is they are in the testing system and like that. The third area we work with is, and we have many projects in that. Again, we are going to discuss that as in the later stage in one of the lectures. The third area we work with is this environment and electronics. That means that electronics are used everywhere today, like as part of everything. If you take car, there is electronics. If you take train, there is electronics. Everywhere there is electronics. And these electronics are getting exposed to the environment. All electronic components are made of metallic materials and things like that. It gets corroded, and it will affect the functionality of the electronics. Sometimes your mobile phone is going bad, means it's due to corrosion inside. And this corrosion is becoming an important thing, and that's what we are looking. We collaborate with many, we have a center in this, and we collaborate with many companies. It's all over the world. For example, Grundfos is a pump manufacturer in Denmark, Danfoss is a power electronics manufacturer in Denmark, Vestas is the wind turbine. There's a big part of Vestas in Chennai, and there is also a big part of Danfoss in Chennai. Grundfos also has a presence in India, that is in Hyderabad. And Bosch has a big part in India. Bosch is the automotive electronics manufacturer, many other things as well from Germany. And SLB is the old Schlumberger, which is the things for the oil and gas, but they also make drilling equipments, and there is a lot of electronics in that. This is from, they joined from US. These are US companies. German company making the polymer materials. Volvo is the automotive manufacturer in Sweden. And like that, we collaborate with many companies in this area as part of the electronics. And this is also one of the key things. But you can also see that in all our work, we have a very, very close collaboration with industries, which also make us our work cutting edge. That means exactly what is needed in the West European program or something like that. And we always work with the cutting edge technologies with this collaboration with these companies. That's our focus. So that's a little bit about us. Now, before I go to this, I want to know about you. And I think we will go and introducing each of you. And while introducing each of you, I also want to know a little bit about how much you know about corrosion and what's your little bit of background, very little about the background as well. And also, why did you come for this course? When you saw this, why did you come for this? Just for fun or something else? Let's just discuss that. You start there. Yeah? Yeah, what's your name? Yeah, and what do you have any corrosion background prior to this, or metallurgy background, or what you do? BTech second year. Where? Here or? In Sikri. Okay, I know Sikri. I've been there many times. And so which area? BTech in which topic? So you have electrochemistry background. Okay, not corrosion, but electrochemistry background. That's good. And why did you come for this course? When you saw this one, what is the reason that you selected this course? What do you expect from this course? Yeah? Yes. And you want to learn more about corrosion. That's the main thing? Yes, it's fine. Yeah. So then you? Yeah. And you are also from the same place, or? Same place and same BTech, same specialization. And you have anything addition to say that, in addition to that, reason for you came for here? Feel free, don't have to worry. This is, you don't have to worry. It is like, I want this course to go in an interactive manner, basically because the reason that I know certain things, but I don't know what you know. And since I don't know what you know, basically I have put together certain slides, and that slides may not contain what you need. The only way we can make, I'll come to know that what you need, and that way we can make it is only if you tell me what you need, only if you ask questions. Then I know that, oh, okay, I could have put that in the slide, and it'll good to discuss like that. So that's the reason I'm asking. So is there anything addition to that? No, that's the same thing. You want to learn about corrosion. What about you? Yeah. 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 So your background electrochemistry. Do you work in corrosion as well? Okay, okay. So what did you come for this course? Yeah. 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 Yes, there is corrosion problem. Yes, 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 yes. This is one of the one of the key areas as well today. People are trying to make supercapacitors, and the corrosion that related to the supercapacitor material is one of the big thing. One of the another university in Denmark, and there is a faculty very much focusing on that. Yeah. Yeah. CS? Sikri, okay. And you do the same specialization as this one. And is there anything more to add to that? You are expecting anything more? Yeah, corrosion. So nobody has looked into the sustainability part of it, or didn't think about that? Yeah, 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 yeah. Yes, yes, yeah. Hope that you will get that. We'll discuss and go. Yeah, 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 yeah. Yes. Okay. So you are familiar with the corrosion a lot. Yeah. Yeah.
Actually a physics student.
Yeah.
My BSc I did in physics and MSc I'm doing in analytic materials science.
Yes.
Now I have come for this course because I am doing project here.
Yeah.
So
Yeah.
I want to know what is corrosion, how it works, and
Yeah.
I am Sukadev,
Yeah.
third year B in mechanical engineering.
Yeah. Yeah.
I came for two reasons. First reason I have a paper, even renewable source of energy. Even renewable source of
Yeah.
energy.
Yes. Yes. Yeah.
Second thing, I can't get good ranks to study at IIT and I want to be in IIT.
Yeah. Here in IT? Yeah. 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 Lakshman. Okay. Okay. Yeah. Yeah.
So my area, I was looking in statistical corrosion
Yeah.
and surface modification.
Yeah. Yeah.
Pretty extreme.
Yes.
So I just want to know about some more modification in terms of surface
Yeah.
industries
Yeah.
and some new modification techniques.
Yeah.
available.
Yeah.
To explore more techniques.
Yeah. 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 Okay. Yeah. 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 Relationship. Yeah. 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 You want to expand more than what you know. Yes, that's also one of the aim of this course as well. Like just go beyond the conventional things, a little bit into these cutting edge things where low carbon technologies and things like that. Yeah. 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 Yes, understand. Yes. Yeah. Yeah. Sikri. Okay. Okay. Yeah. And you have experience in corrosion or a little bit? Electrochemistry, you know, because you are studying this specialization. Same. Yeah, and same specialization you have. So then you also know a little bit of all of you are in which year in the BTech? Second year. Okay, so it's more or less started. Yeah. Okay. Okay. Yeah. No more. Yeah. 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 I didn't get. NID Calicut. Yeah. 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 Yeah, you want to expand your knowledge. Yeah, I understand. Yeah, yeah. 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 Are you, is corrosion is a part of your research or going to be? Okay. Okay. I didn't get the VIT. VIT is in Vellore Institute of Technology, right? Yeah, yeah. I had students from PhD students from there. Yeah, yeah. 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 Civil engineering. Yeah. Yeah, yeah, yeah. That's one of the important thing. Yes. Yeah. We also work on. You will see that when we go to, I'll not show so much. When we go to the carbon capture and storage, in the carbon capture and storage, one of the corrosion issue is cement metal interface, similar to the concrete, because once the CO2 is filled in the well, they close it and put a big layer of cement and close it. And then there's a cement metal interface outside like the concrete problem. And we are entering into that, we are looking into that. It's not easy to do research in that. Yeah. 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 ARCA is a Hyderabad, I think, right? Yeah, 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 yeah. Yeah, yeah. To learn more. Yeah, yeah. 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 Rebar. It's here. Okay, yeah. Yes, yeah, okay. Yeah. Yes. Yeah. Yeah. Yes. Yeah. 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 Two more. Yeah. 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 Okay. Okay. Yeah. 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 Okay. Okay. Yes. Raja's group. Yeah, I was there last week. Just 3-4 days I was there. Yeah. 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 And once again, thanks for receiving me in the airport. Yeah. 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 Yes. Yeah. Understand. Yeah. 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 Think with that everybody introduced, right? Anybody missing? No. I think that's it's also the reason that this introduction you can see that there is a wide background here. There are PhD students already working in corrosion, and there are students probably having a little bit experience on electrochemistry and various other background as well. And this is always the problem also for the teachers whenever we teach. It's extremely difficult to teach at a particular level, because when if I take the advanced corrosion level, then some of you will not get it. If I go into the very starting level, and some of you will be knowing that. But we need to start with the basics, and we will try to sim through somewhere in between, and that's what we will do in this course, so that everybody get something, and that should be the aim of this course. That's also the reason that I'm saying that it has to be an interactive course. Don't worry that is what you are asking the questions and you are interrupting me, and you need to do that. This is what I like. And just interrupt and ask questions, because then only I will know that, where I fault in my case. As I told you that I know different things, so I may not have put together all the things what is required. So please ask questions, and we go in an interactive manner. So that's the aim of this course, okay? Let us do that. So aim of this course is that this corrosion prevention control. I think everybody agree that today the corrosion prevention control is viewed as an integral part of the sustainable development to the huge loss of resources that can result from uncontrolled degradation of materials. Any field if you take, you can take that any field if you take, and loss of materials means many ways it will affect the technology. It can, because you have to change the material, that way there is a cost involved in that. When the material is failing means a wind turbine is failing, wind turbine has to shut down for a long time, and that also makes the loss, and that way there is. So corrosion degradation of materials and system cause huge loss of resources, economic damage, ecological cost, energy loss, and therefore proactive use of better materials design and protective measures to reduce corrosion is an important thing. Equally important is a corrosion monitoring part, that is using this big data information, proactive design and maintenance strategy in order to optimize maintenance costs and enhance performance during the product life cycle. So it's not just the corrosion prevention. That means that material loss, because the material loss, the system is failing. So that way there is repairing work and things like that. All those things are there. In order to do that, a proactive maintenance is also important. Understanding that how the corrosion can occur. A typical example I tell you, which I'll also come later. There are so many wind turbines all over the world right now. I think India is also catching up in the wind turbine. In Denmark, almost 40% of the energy is produced by wind turbine. Because why? It's a clean energy, right? It's a clean energy, less carbon dioxide emissions, so 40% energy is produced by wind turbine. And where to put this wind turbine? The best place to put the wind turbine is in where? Huh? Somebody told. It's not. The best place to put a wind turbine is in the sea, because offshore. So that's the reason that if you go to Denmark in the seaside, you will see that there are so many offshore wind turbines. But what is the issue? If you put a offshore wind turbine, corrosion is the biggest problem in the offshore wind turbine. Now corrosion occurs, so you need to take care of this. We can use the better materials and things like that, as I mentioned. But in addition to that, another problem is that I want to come to the third point. If a wind turbine is having a problem, one visit to wind turbine is from taking a helicopter and visit to this wind turbine, offshore wind turbine, is around 50,000 pounds. I don't know how to convert. I'm trying to convert that in rupees. That's the kind of cost in one visit. So that means that if you can have a proactive understanding, like putting a sensor, corrosion sensor, and you know that how much corrosion is occurring. So that means that they can plan. They can say that, okay, anyway we are going to have a visit. This part is almost corroded, and better to change that as well, like that. And that way they can reduce number of visits, and that way this proactive maintenance strategy is also important. And this is the way we are going to look at this. Only thing is that we will take different sectors. So if you look at the corrosion program, this program here, we have a set of theory lectures, and where I will give an introduction today on this connection, and then Lakshman will also give a little bit of an introduction to the basic theory of corrosion, which is important, and those who are not familiar with the corrosion to little bit to understand basic theory of corrosion and corrosion testing, And then we go from tomorrow, we take different sectors like this. That is protective solutions and sustainability, material recycling and sustainability. Um, there are metals used in the architecture that's also causing problem these days, and things related to the and corrosion prevention in low carbon technologies, electronic systems, how that is causing the problem, and proactive design. The proactive design just we discussed, proactive design part. So all these things we look from the point of view of the sustainability, because all these are actually connected. We don't have to connect it, but actually connect to sustainability, and that we're going to look. There are also short practical sessions here, and that's why I mentioned here as well the 5 days of theory and practical myths. And of course, the practical session in any course is always difficult, because this many students having in the lab and hands-on experience is not easy. So the practical session is actually meant for not to learn so much with the practical, but it's much more to have an interactive session. Like, let us discuss there. So there is a little bit more of a free atmosphere and for us to discuss, and that's more aim of the practical session. That's also we put this kind of posters at different places, which also you can go through it, and it also raises some questions, and that way we can make it as that is kind of an interactive session for the sample. So I just start with a little bit of giving this connection, so importance of a little bit of introduction to the corrosion, and I will not go into the electrochemical theory part that much, but that Lakshman will do later, and then I will connect that to sustainable technologies and things like that. So I think we start with the basic. What is corrosion? The corrosion can be defined as the degradation of materials, right? Any materials, not necessary to be metals. Only thing is that we are focusing in this course, we are focusing more on metal, but in general, any metal, and that is can degrade with interaction with the environment, and that's what we are calling as corrosion. It can be metals, it can be polymers or ceramics. Polymers also can degrade. It can absorb moisture, it can hydrolyze. The bond can be broken. That way it can have problem. UV light also will create a problem for polymers. All paint companies, they do a lot of UV testing of the paint, because the paint surface is exposed to UV light. With time, the polymer molecules can degrade, and that way it's important. Ceramics is comparatively a stable material in normal sense. The problem is very aggressive chemistry in that case, right? Like big acid, sulfuric acid, and things like that also can attack ceramics or high temperature degradation. So even polymers and ceramics can degrade, but we are going to focus much more on the metals. So if you take the metals, metal also can corrode in interaction with the environment in different ways. So mainly we divide the corrosion of metals into two categories. One is we call it as a chemical attack, where we don't think there is water present. There's no water, it's a dry condition. We have chemical attack. Another one is we say that it's wet conditions. It can be a bulk water or thin film. There is water present. Then we call it as it's an electrochemical corrosion, another mechanism. This is what we call. Although this boundary is very vague, because you will not see any surface without water. Most of the time, even if you have a 60% humidity, there is a thin layer of water on the surface. So having saying that there is no water here is not a correct thing. So mostly this boundary is very vague, very diffuse, because this one also can have a water film present. But in order to differentiate the mechanism, we can say that there is dry corrosion where there is a chemical attack, and when there is a electrochemical process. So just to see, that is, what is this corrosion which we are talking about, and what is the basic parameters which is determining this corrosion problem. So we see this brown color rust, right? We see everywhere. You just go out, if you look around, there is a brown color corrosion. Thinking that how we can represent that brown color corrosion in a simple way, basically it is steel, is made of steel, which interact with the air, that form the rust, right? That's what is happening there. If I take a little bit more in a little bit more detailed manner, we can say that there is iron, there is oxygen in the air. I don't bring the water now, we keep the water for later, and there is oxygen in the air, and that react and form iron oxide, and that iron oxide is the one which we are seeing it as the brown color rust, right? This is what is happening. The metal is reacting with the oxygen in the air and forming the iron oxide. But why this is happening? Can we completely stop corrosion? Can we completely stop corrosion? Why? It's correct. Answer is correct. Is that the reason that you cannot stop completely the corrosion? It's inevitable. Why it is inevitable? Sorry? Why it is natural phenomena? But that doesn't mean that it could happen, right? It cannot be totally removed. That's coming to that. Inherently outside the stable state. I want to put that in another word. That means that thermodynamically outside the stable state. So that means that thermodynamically corrosion is a feasible process, a spontaneous process. So you cannot stop the corrosion, you can only control it. Right? So not only corrosion can be controlled almost to a zero level, but you cannot totally stop the corrosion because thermodynamically it is a feasible process. So if you put it this way, that is, how can we understand that? Think about the metals. There are so many different metals. How it is available in the earth? How metals are available in the earth? Ores, right? It's a compound. It's not pure metal. The only gold you can see as a pure metal, but all other things are existing as a compound. And from that we are extracting these metals, right? Taking the ore and extracting the metal by spending energy. So if you want to make iron, you take an iron oxide and you heat it with carbon. By providing energy, iron is separated and carbon will take the oxygen and make it carbon dioxide, iron is separated, right? So always we are making the metal from this stable state into an high energy state. So always that will have a tendency to go back to this lower energy state, because in this world, whether it is a chemical process, whether it's a physical process, everything is trying to achieve the lowest energy state, right? Think about hydroelectric power. So you have water which is stored here. Why this water has to flow? Because that's the lowest energy state. The potential energy of water is high here, potential energy of water is lower here. If you open here, water will flow because it has to want to achieve the lowest energy state. So everything, all whether physical or chemical process, everything want to achieve the lowest energy state, and this is also the case with here. If you want to achieve the chemical energy wise, it has want to achieve the lowest energy state. We cannot stop this, right? We cannot stop this, but you can control it, because how much water is going down depends upon how much you open it. So that is we can do. So you can control it, but you cannot stop it. So when you are reducing this one, you can control the water flow. What is that parameter called? That's a kinetics. So one is the thermodynamically corrosion is a feasible process, but you can control the kinetics, and that way you can reduce the corrosion behavior, right? You're taking this example into this. But you cannot, because it is a high energy state, except the gold. Take that little bit more into this. So we have seen earlier that iron is oxidizing, iron is reacting with oxygen and forming iron oxide, right? Let us see that this is a feasible process. Thermodynamically means you can do certain energy calculations, and energy calculations should show that as a feasible. So this is what we are expecting, that is iron is having a higher energy. When the iron oxide is forming, it is going to the lower energy state. I did some calculation. So what is that energy? Energy is a free energy, right? Everything has a free energy content or free energy state. Free energy state, free energy is a sum of, just to think and understand, free energy is a sum of, Helmholtz free energy is a sum of two parameters. What is that? Entropy and enthalpy. So it's a sum of enthalpy and entropy, right? Doesn't matter. I just want to know. So the free energy content of every, so this has a free energy content, this has a free energy content, this has a free energy content. So if you do a summation process, we know that what is the change in the free energy here. That's what I did here. I did at minus 100 degrees centigrade, 100 degrees, because this is temperature dependent. 100 degrees, and I did this free energy calculation. You can see that in all these cases, when they change it to this one, I get a negative free energy change. What it shows that is, whenever negative means, this process is changing it to this, because this has the lowest energy state, energy is liberated. Energy is liberated means negative. So that means that this is a feasible process. Thermodynamically, this is a feasible process. Iron will change into iron oxide. Take another example. Silver is reacting with oxygen. So again, I did the free energy calculation, but there is a nice thing you can see here. 100 degrees, minus 100 degrees centigrade to 100 degrees centigrade, you have a negative free energy change. But temperature from 300 to 500 degrees centigrade, I have a positive energy change. What it shows is, up to 100 degrees centigrade, reaction goes in this direction. Above that temperature, reaction goes in this direction. That's what it shows, right? Because silver is, we also know that silver is less corrosive than iron, that way. And what's the good thing about that? You must have seen that all these silver ornaments, you may have some silver ornaments in the house. After some time, it becomes a dark color. You want to bring back. What you do? Take a torch, blowtorch, and blow it on it until you reach that degree centigrade. You will see that it is clean. Because now the reaction has taken place in this direction, silver has returned back to the original state. There are many other ways also to do it. You don't have to heat it and spoil it. There are many other ways also to do it. But I just, as an example, you can change it. So again, you can see the thermodynamic aspect here, right? That is, thermodynamically it is stable, then that process will take place. So without taking more time on that, let us bring the water now. Now, until now, we don't talk about the water, we are talking about oxygen. So we are bringing the water. When you are bringing the water, thermodynamically everything is the same. Thermodynamically, everything what we are talking about the same. It is a feasible process, then the reaction will take place. Only thing is, when there is water, the mechanism of corrosion is different. We call it as electrochemical process. So that way, the way it is taking place is different. This is the only thing that changes with water. So when you have water, we can say the corrosion process is exactly similar to a dry cell battery what you are using. The battery is working because of corrosion. Only difference between the normal corrosion, battery corrosion is, in the case of battery, we are allowing it to corrode in a controlled manner, and that is producing the electrical energy. In the corrosion process also, electrical energy is produced, but that is, we don't want that, because then your material is degrading. That's the only difference. So the battery, you can take it as an example. What do you do in the battery? You have two electrodes, right? In the battery, you have one electrode, positive electrode, and you have a negative electrode, and you put an electrolyte in between. If you connect between these two terminals, you get a current, right? You get a current, and you can a bulb will glow, or what other things you want, you can do. If you think about what is happening inside, one of the battery I took, so there is a zinc electrode. The zinc electrode will dissolve as zinc 2 plus ions plus 2 electrons. That's we call it as oxidation or anode reaction, because whenever this electron is generated, we call it as oxidation. Then there is an electrolyte here. This electrolyte contains these ammonium ions. Whatever electrons produced from the zinc is used here in this place. This one will take the 2 electrons and form the ammonia, and that way the circuit is complete. 2 electron is produced, 2 electron is used. 2 electron is produced here by dissolution process. It comes through the external circuit to this one, and the 2 electron is used here for this reaction. That electron is coming through the external circuit. If you put a bulb, it will do the work. It will glow the bulb, and that electron comes here and then do this reaction. So the circuit is complete there. So one reaction is producing the electron in an electrochemical process, other reaction is consuming the electrons. Or we can say that there is an electron transfer between one electrode to another during this process. So that's the reason that we also call electrochemical reactions as charge transfer reactions. Charge transfer reactions. Those who are studying electrochemistry, you must have learned this terminology. Charge transfer reactions, because charge is transferred from one electrode to another. So that's the reason that's charge transfer reaction. So that two half, and each of these reactions we call it as half reactions, because it's not complete, right? This will not be completed without this. So that's the anodic half reaction. This is the cathodic half reaction. Or this is the half oxidation reaction, that's half reduction reaction, like that. So that's combined with that one. This is exactly the meaning of the corrosion as well. So in this case, we are doing in a controlled manner, and if you sum up this energy, you have a negative net delta G change that is negative. That's the reason that this is happening. If you take that into a corrosion, so that means that before we go to that a little bit more, we talk about free energy. So earlier we told that iron has a free energy, oxygen has a free energy. The free energy equivalent of electrochemistry is the potential. So what is that potential? If you take a metal and you dip into a solution, a surface potential will develop. This surface potential, whatever is developed, is a function of the free energy. So free energy equivalent of the electrochemistry is a potential. So that means that if you are measuring the potential of an electrode, which is equivalent to measuring this free energy. How we can measure a potential? If you want to measure a potential, you need another electrode. Like in the socket, if you want to measure the potential power in that socket, you cannot do it just by inserting one knob. You also need to insert another one, right, in the multimeter. What we are doing is one hole there is ground, another one is the positive terminal or with the potential. So we are measuring the 230 volts with respect to the ground is 0. So always in order to measure the potential, you need reference. So here we are using a hydrogen electrode as a reference, and hydrogen electrode potential we are taking it as 0, like the ground, and with respect to that we are measuring the potential of this in a standard condition. Standard condition means this solution is, if we are measuring the potential of iron, this solution will contain 1 mole of iron ions, like that 25 degrees centigrade, there are conditions like that. If we measure that potential, we call it a standard electrode potential. The standard electrode potential you can compare exactly with the standard free energy. This is a relationship. That standard potential, that's what we listed here in the electrochemical series, which probably Lakshman will be coming more into that. This potential level here, like we say that if from the top to bottom as we go, material is more corrosive. So you will see gold, which is less corrosive. As we go down in the potential here, the material becomes more and more corrosive. So this potential value itself shows that which one corrode more. If I take a metal here, I can say that this metal is far below, this metal will corrode more than the other one, because that represents the free energy, like that. So this itself is an indication, the potential value as an indication, but I think Lakshman will come more into that. I think next question he will come. So that means that if you are coming back to our battery analogy, you are taking a metal from here. So there is iron, and you are taking a metal from here, say copper, and these two you are putting it together in a solution, sodium chloride solution. You are putting these two metals together, just to show that how when you are coupling two metals, how it corrode. If you put this, that's iron, that's copper, you are putting a voltmeter there. You read the voltage around 0.78 volt. Yes. Why you read 0.78 volt? Because I didn't show it as a difference. Take the potential of this one, copper. Take the potential of iron, that's here. If you minus that, you get 0.78 volt. That's what you read here. What is the connection between? So that's the reason that 0.78 is coming. So there's potential difference between these two. I told you that potential is equivalent to free energy. What is the relationship between potential and free energy? If potentially we show it as E is equal to minus NFG. This is the relationship between free energy and potential, where N is the valency of the electrons, corresponds to the reaction, F is a Faraday's constant, and what it shows here. Now G, that means that G is equal to E divided by minus NF, right? What it shows, whenever this one is positive, this is negative, right? So here I summed up the potential of iron and copper what it shows that is that potential if you put here, G is becoming negative. So that means that in this case, this reaction is feasible like this. So that means ion will corrode, electron is produced, that electron will be used here for the cathode reaction, and that way the reaction is complete, and that way the corrosion can take place. Copper will act as a cathode in this case, iron will act as an anode in this case. This reaction is feasible, for example, in the presence of water. So that means that, what I mean is that if I connect a wire between these two, exactly like what happened in the case of battery, I can get an electron flow, a current, and this will start corroding because during that current, this produces an electron. That electron will come here and is used for the cathode reaction. When I short circuit this, it gives a potential somewhere in between of this value. We don't have to worry so much about that, you get a corrosion potential. So what I want to show is that here you have two different metals like iron and copper, which couple together, which comes from the electrochemical series with a difference. And that difference make one of them is to act as a anode, the bottom one, and copper is a cathode which is above that, and that way you get the corrosion of the iron. For example, this is an electrochemical process where you have two half reactions. One reaction is producing electron and other reaction is consuming electron. What is this reaction? This is called oxygen reduction reaction, which is one of the most feasible cathode reaction in any media, because always any water if you take, there is oxygen in it. So that oxygen can take these electrons and form like this. So that's the reason that this becomes the cathode reaction always. That's the most easy cathode reaction. Now I'm showing the corrosion of iron when it's connected to the copper. But when you look around, you don't see two metals. There's an iron surface that's corroding. This is just for that to show that how the electrochemistry works. Electrochemistry works with two electrodes. One can act as an anode, another one is act as a cathode. But it's not necessary that always you need a separate metal. Of course, separate metal can be there, but it's not necessary. So if you look around, you will see that just iron is corroding. You don't have a second metal. That's because these two things, whatever I'm talking about, these two metals here, it's not necessarily two metals, because on the same metal surface, some area is acting as anode, some area is acting as cathode. And that also changes with the time. So that way it will keep corroding. Always what will happen is, so if you look at here, this area is acting as anode, some of this area is acting as cathode. So electron is produced here, that is consumed here. So all these process of electron transfer, as I showed here as a two anode and cathode, where electron is produced here and is consumed here, it is taking place on the same surface. But microscopically, if you look at it, you will see the anode and cathode. So it can be on the same surface, is not necessary. That is just for the electrochemical representation we are showing is two different electrodes. And that's the reason that any metallurgical microstructure if you take, it's corroding. Take the case of stainless steel. Why the stainless steel is corroding? There you can have the manganese sulfide inclusions. Steel part, manganese sulfide inclusions. This manganese sulfide inclusion is acting as a cathode, and the steel part is acting as anode. So the cathode reaction will take place here, anode reaction, metal will dissolve here. This will corrode, this will act as a cathode. This is a recycled aluminium. Recycled aluminium contains a lot of iron because as an impurity. This is what we are going to discuss later. That impurity iron will make this kind of intermetallic particles. These intermetallic particles, because of iron, if you look at the electrochemical series, aluminium is coming here, iron is coming here. So aluminium is more active than iron. Because of that, if these two are coupled together, this will act as a cathode and this will act as an anode. So here, in this particle will act as a cathode, this area will act as an anode. So that means the aluminium area will corrode, iron will act as a cathode for the cathode reaction. So it's not necessary that two different materials together. On the same surface, you can have different material. In the case of cast iron, there is graphite and iron part. Graphite will act as a cathode, and iron part will act as anode, like that. So this is the importance of the metallurgical microstructure. All metallurgical microstructures are heterogeneous, which means that automatically there is anode and cathode on the same surface, and that causes this corrosion problem. That's what I schematically shown here. So in a stainless steel substrate, you have the manganese sulfide inclusions. So iron part will dissolve as iron 2 plus, but that electron will be used in the manganese sulfide inclusions for the cathode reaction. So you can see that on the same surface, both reactions taking place and the corrosion is occurring, like that. I think you will also talk about the galvanic series, right? Probably, yeah, I will leave that here. Now let us look at just that introduction of the corrosion. Let's just look at the corrosion and economic impact. So whenever we talk about corrosion, there's a big loss due to the corrosion because corrosion is everywhere, irrespective of sustainability part. Sustainability part is probably coming now, but always there is corrosion is making big losses. We can say that it's direct losses and indirect losses. Direct losses is component is replacement or material replacement because failed. So you need to change that. Indirect loss is, for example, when because of corrosion, wind turbine gear system has corroded. Gear system is, or electronics have corroded. It's not working. So that means that 3 months they have to shut down in order to repair. So there's a loss related to that. That's what we call it as indirect losses. Altogether, if you take it in the developed countries, like around 3.5% of GDP is a big amount that is used for corrosion control, bridges, and many things like that. It is lot of money is spent on that. This is what I mentioned, that a typical example of a costly intervention for corrosion maintenance of offshore wind turbine, which costs around $50,000 US in Europe. One visit to offshore wind turbine. So if you can reduce one visit to wind turbine, that itself they save a lot of money. By knowing that corrosion can occur, so what they do? For example, Vestas is a wind turbine company. They want to design the wind turbine. They don't design the wind turbine same way for everywhere. If they are designing a wind turbine which is has to be placed in the land, they know that before they make the wind turbine, they know that that land area has a corrosion class which is C3. C3 is a lower corrosion class. It will not corrode that much. What is a corrosion class? Different things corrosion class we have. If you go from the inside this room into the offshore condition, what is the corrosion class? We have. Inside this room, corrosion will be mild, right? That is, we call it a C1 class. Then as we go out, it increases. When we go near to the sea, it becomes C5 class. To the sea, when we call it as CS class, which is a little bit higher than C5 class. There is a lot of corrosion there. So that means that if Vestas is designing a wind turbine for land, probably the condition there is only C3. So they use the material protective system, everything is according to that. But on the other hand, if they are designing a wind turbine for offshore, they have to design it with a CX or C5 in consideration. So they use different materials and protective systems. That means that a wind turbine which has to be sold, it has to be placed in the offshore, will cost higher than the land. So they need to know all these things. That is, what is the corrosion class there? And knowing that corrosion class, if they design for C5, they also will reduce the maintenance. Think that a C3 turbine, which is meant for the land, is selling and installing in the offshore. They will have many visits like this, right? Like that. So that's an example. And large amounts of steel and other material wasted due to corrosion and costing huge amount of money. In India, it is around 2.4% of the GDP. You can see that. It is 2.4% of GDP is spent on this in India. You can also divide that into different things. So you can see that there's a kind of a division showing that it is every sector if you take. There are many things if you take here. Everywhere there is corrosion problem and losses. So that's the importance that we need to take care of the corrosion. Just an example, I took it here to show you that sometimes a small component, how that can create problem. This is the F-16 happened in Europe. F-16 crashes. 5 of the F-16 has crashed And that means that the cost of that, this one is around this much. You can count how much it is. And why this has happened? Because one problem discovered by this Kelly AFB engineer trained the corrosion controllers corrosion the tin-plated electrical connection pins mated with the gold socket. So that means that somewhere on this product, there was an electrical connection. That electrical connection, one part is made of tin, other part is made of gold. Is it a good combination? No. Because if you look at the electrochemical series, you can see that gold is a very noble metal and tin is unnoble metal. So that combination of this gold and tin together has caused a corrosion problem. Because of corrosion, electrical connection is not good. That electrical connection is not good means it affects the control systems because the power is not provided properly. That control system made these crashes. This might cause, cost of this one will be, this component will be less than $1 probably. Less than $1 component in an F16, 5 F16, you can see that how much is the cost. That's the importance to take care of even with that small component which costs $1 because $1 component corrosion can cause probably 1 million loss. And that's the case. That's an example here. So now, as I mentioned that the corrosion is also becoming important with sustainability, which we will discuss in the upcoming lecture. So I just only put here is that, for example, related to the architecture, because in Europe, from 1990s onwards, there is a lot of thinking about what metallic material is used in the different architecture, because think that because of the rain and pollution, material is corroding and it is coming to the earth. Think about copper. Especially in Europe, you will see that there is a lot of copper roofing. In old buildings in Europe, everything is, the roof is made of copper, which you will see green color because the copper patina has formed over the time and it is coated. But the cities, there is pollution. What pollution cause? Because of pollution, what happens? You can have acid rain. Because of pollution that is dissolved in the rainwater, you have acid rain. That means the pH of the rainwater is reduced, and that means that all these copper products are dissolving now by the rainwater. Copper is dissolving coming into the earth, and copper is not good for the biological systems, and it creates problem. And there are many other elements which comes to that probably is poisonous as well. So there is a lot of thinking about what is the material used, how much material is coming out and things like that. So this is one of the things which is increasing and increasing, and that is one thing. One connection to sustainability which we will discuss later. Another one is the recycling. I take the aluminum recycling as an example. As I mentioned that everybody want to replace the steel with aluminum. Why? Because of the lightweight. What is the density of aluminum? Or what is the difference between the density of aluminum and steel? 3 times. So density of steel is almost 3 times that of aluminum. So that means that what it means from the application point of view. If you have 2 alloys, one alloy of steel and one alloy of aluminum having equal strength levels, if you make with aluminum, it will weigh only 1/3. Weight can be reduced by 1/3. A 100 kilo component, if you make with aluminum, it will weigh only 30 kilo. So that means that there is a lot of interest today to use aluminum in the electrified all cars, petrol cars, and much more in the electrified cars. Why? Because electrified cars, petrol, you can put 60 liters of petrol in a car and you can drive for 900 kilometers. A Tesla, even with the Tesla, you cannot drive for 900 kilometers. The maximum mileage Tesla gives is probably 400. And in Europe, even you don't get 400 because Europe is very cold. And you think that at 0 degrees centigrade, you are driving a Tesla, there is a lot of discharge. And also the electricity has to be used for many other things. So if you want to get the mileage, the only way you can increase is you increase the amount of the battery. Or we can say that reduce the weight of the car. When you reduce weight of the car, the energy spent is less per kilometer, and that way you can get a bigger mileage. Reducing the weight of the car also you can turn another way. If you reduce the weight of the car, you can increase the battery weight because still you come to the steel car weight. So this is the concept, and that way the aluminum should be the material for all electrified cars. And then what is the problem? The cost of aluminum is much higher than virgin aluminum, much higher than steel. The only way you can do that one is recycling, but recycling and introduce much more metallurgical issues in microstructure that is corrosive, and this is what we are looking at. How we can optimize the microstructure. If we cannot optimize, how we can make a better protective coating, useful for the recycled material and things like that. This is another issue. Carbon capture and storage, I mentioned that is they want to put the carbon dioxide into the storage, and as I mentioned that this carbon dioxide has to be captured and made into a supercritical state which occurs at a particular temperature and pressure level. And this supercritical state, carbon dioxide in a supercritical state is not corrosive. Carbon dioxide is a benign. It's not corrosive, but the problem is that whenever you are capturing carbon dioxide, it contains impurities. If they are capturing the carbon dioxide from power plants, cement plants and things like that, it contains a little bit of moisture, water. It contains H2S, it contains SO2, it contains NOx gases. Think that you have a 1 liter of supercritical carbon dioxide. Supercritical carbon dioxide, you can take it a liquid carbon dioxide. Out of that 1 liter, you have 1 ml of water. Doesn't sound that much, right? But you need to think in another way. That carbon dioxide also has a lot of H2S, SO2 and NOx gases. When there is water, H2S and SO2 and NOx gases, what happens? Acid. Because this H2S and SO2 is going to dissolve in that small amount of water and create an acidic condition. Sulfurous acid species will form, nitric acid species will form and things like that. Now you have to think that you have only 1 ml of water and you have the dissolved gases, and that will make the pH very low. So that means that although you have 1 ml of water, but you have that 1 ml of water with a very acidic pH. And when it is pushed through this one to the well, all these are made of metallic tubing, and all this metallic tubing will get corroded. And these issues and different levels. We will discuss more in detail later, but just to introduce that, again, those ones are the bottleneck is a corrosion problem. And once the CO2 is injected, this well will be closed, and you can see that they expect this well to be safely there for many 100 years and without any corrosion problem. Wind turbine. Offshore wind turbine, if you take it, there is lot of corrosion issues at different levels. There are things which is below the earth, structures. There are structural part which is just above the sea, where there is a splash zone. Things can be splashed. That kind of things, which there is another corrosion problem here. And then you take the atmospheric part where there is nacelle, and inside the nacelle there are electronics, there are other components and everything. There is atmospheric zone and the corrosion problem. It's also the case with if you take the solar energy and things like that, which is also exposed very near to the sea. Again, there are many corrosion problems there, and the technology is dependent on that, the corrosion prevention part. It's also the case with other energy storage system like geothermal, hydrogen production and storage. If you take today, people are trying with the molten salt for the energy storage. You melt the salt when there is power, and why all these things are needed, these energy storage systems? Because when you have wind turbine, when the wind turbine produce energy is not fixed. It depends on when there is wind. So when there is wind, you produce energy, and when there is no wind, no energy. So that means that when there is wind, there is excess energy. So Denmark produces 40% of the wind energy I told you about from wind energy. When there is wind, there is excess energy, they just transport to Norway. And Norway says that we don't want anymore and just wasted. On the other hand, if we can have a storage system, that way we can store that energy and we can use it later, and then that is a good thing. That's the reason that everybody is looking for hydrogen production or this molten salt and things like that. Again, there is a lot of materials used there, and there is corrosion issues. Electronics. Electronics are everywhere, part of the wind turbine, part of the automotive and things like that. All these electronics contains electronic components which contains lot of metallic materials which corrode, and affects the functional issues of the electronics, again create efficiency problem and things like that. This is another thing. We will discuss all these things. So that just I showed the slides, but we will discuss all these things. So that means that you can see that in a circle, it is getting connected to all kinds of sustainable technologies and development. So this sustainable development goals of the United Nations, if you take, at least you can connect to, it can connect to many other things, but at least wherever I put this green color arrow, you can connect to that. Affordable and clean energy. If you want to produce, corrosion is an issue there. Climate action, because climate, if it is also affected by all these technologies, and corrosion is important there. Life on land, metallic components, that's what we are discussing about the building. The leaching of the material, how that is contaminating the environment. Industry innovation and infrastructure, it is affected by the corrosion. Again, that's a part of this one. Good health and well-being. Many of the things what we are trying to do is corrosion related coating technologies they are trying to remove is because it's carcinogenic and things like that. Sustainable cities and communities. Again, I was talking about the material leaching out from the building and all those things, how is contaminating the cities and things like that. Responsible the consumption and production. We have to be responsibly consume the material, which that means the corrosion has to be less. Again. And the clean water sanitation. Again, the clean water related, contamination and things like that from the corrosion problem. So at least all these things we can link to the corrosion problem, these UN sustainability goals, if not other ones. So that's the summary of this part. I just want to give that corrosion is very important to sustainable world because corrosion is equivalent to preserving the resources. Corrosion can lead to big losses and accidents, hence most important to take care. All in general means loss of resources. Corrosion is becoming an important part of the sustainable development technologies and products, for example, architecture, recycling, we discussed many of these things. And hence corrosion control, prevention and prediction is most important today. Actually, a terminology is developed today. It's called in this proactive design and prevention strategy. It's called PDMS. That means anything you design, as I talk about the wind turbine, think about corrosion. So that's a proactive design. Think that corrosion can happen. So how to design? What material to use? Design is an important part which you will see later. How to design for a less corrosion and at the same time having a prevention strategy means it includes also corrosion monitoring, what I mentioned, and understanding that how my materials are corroding and that way to take preventive actions and things like that. So that terminology is developed as called PDMS. So everybody talk about, yes, wind turbine, we use the PDMS, which means that this is the thing that proactive design and prevention strategy. So those last slides we'll be looking at again into a little bit more detail in other lectures. It's a magnitude. It's a minus and magnitude both. So that means that if there is a reaction giving a free energy changes as -2, another reaction giving free energy changes -200, which means that both are thermodynamically spontaneous and feasible, but -200 is much more feasible than the -2 to that extent. We are not to thermodynamic because that thermodynamics is to show that whether the reaction is feasible. Whether the reaction takes place or not, that depends on the kinetics part. Exactly what I was talking about the water, hydroelectric. When water is at top and water is bottom, because the potential energy change, thermodynamically we can say if there is an opening, water will fall. At the end, whether the water will fall or not depends upon how that opening and how much is that opening. That's the kinetics part. So thermodynamics tell us only the feasibility or spontaneity for the reaction, but not the how much or what is the rate of process. No, that's why it doesn't show that it is -200. It will occur more. It's not showing. Only thing it shows is that this -2, which I showed with the example of silver. If you have a free energy change of -2 in one case and -200 in another case, what you will see that if you increase the temperature, it will change the other way. That's what it shows. So energetically, the -200 is more favorable for the reaction to occur. That's all. No, it's not conflict because it doesn't show the rate. It just only shows the feasibility. No, more feasibility doesn't mean that more rate. That's the point. Rate is dependent on many other factors. Probably Lakshman will be talking about that in his lecture. It's only theoretical. That's the problem. Because the reason is that you cannot produce 100% because even if you make a pure material, but still there is surface defects. Like if you are just polishing, that itself will create a surface defect, which some area can act as anode and cathode. Theoretically, you are right. Yes, if you have a homogeneous material, then there is no micro cathodes or anode, and then corrosion shouldn't take place. Yeah. I leave it to you now.